Welcome to today's paper reading. Today's paper is titled, Never Miss a Beat, an efficient recipe for context window extension of large language models with consistent middle enhancement. This paper, authored by Tong, Yanpeng Zhao, and Zilong from Beijing Institute for General Artificial Intelligence, presents a method for extending the context length of large language models. It is currently under review. The abstract discusses the challenges in extending the context length of pre-trained large language models, LLMs. Existing methods often require fine-tuning at very long target lengths and struggle with effectively using the middle part of the context. To tackle these issues, the authors introduce CREAM, a method that interpolates positional encodings by manipulating position indices. CREAM is designed to be simple and training efficient, requiring only fine-tuning at the pre-trained context window, such as Llama 2-4K, and can extend LLMs to much longer target lengths, like 256K. The method also introduces a truncated Gaussian to focus more on the middle part of the context, addressing the lost-in-the-middle problem. Experimental results demonstrate CREAM's success in extending both base and chat versions of Llama 2-7B to the target length, ensuring never miss a beat. The authors plan to make their code publicly available soon. Figure 1 presents the results of applying various position interpolation methods to the lost-in-the-middle task using CREAM and POSE. The data clearly indicates that CREAM surpasses POSE in performance across all positions, with a notable enhancement specifically in the middle section of the context. This comparison highlights the effectiveness of CREAM in addressing the challenges associated with long context processing in large language models. Transformer-based large language models, LLMs, are typically pre-trained with a fixed context window size, such as 4K tokens as in Tuvern et al. However, many downstream applications require significantly longer contexts, up to 256K tokens. P-based methods offer a solution by extending the context window without altering the model's architecture. The proposed CREAM method aims to efficiently extend the context window while optimizing the model's ability to process content in the middle of extended contexts. CREAM introduces a novel fine-tuning recipe that includes Gaussian middle sampling to prioritize middle content, addressing the lost-in-the-middle challenge. The methodology section outlines the approach to extending the context window size of a pre-trained language model from N to L, where L is greater than N. This is achieved by efficiently learning from a small-scale training dataset train. The process involves maintaining continuity and positional encoding, which is crucial for preserving the model's performance. Additionally, the relativity and positional encoding, specifically using rotary positional encoding, ROPE, is emphasized to ensure the model can handle relative positions effectively. The proposed method, CREAM, divides the context window into 3 segments: head, middle, and tail. 2 segmentation strategies are employed to balance continuity and relativity. Finally, a truncated Gaussian sampling method is introduced to focus the model's attention on the middle part of the extended context, enhancing its ability to handle long contexts. Figure 2 illustrates the process of CREAM position interpolation. The pre-trained context window is segmented into 3 parts: the head, middle, and tail. To ensure continuity, the lengths of the head and tail are fixed to a small value k. For maintaining relativity, the lengths of the head and tail are set to n/3. The middle segment start and end position indices are determined using truncated Gaussian sampling, which helps the model focus more on the middle part of the context. The authors extended the context window size of Llama 2-7B and Llama 2-7B chat models to 32K, creating CREAM Base and CREAM Chat. They evaluated these models on several benchmarks including long chat lines, lost in the middle, and needle in a haystack 2. The primary baselines for comparison were RANPOS and POSE, which also manipulate position indices for context expansion. These benchmarks and baselines were chosen to ensure the extended model's performance was thoroughly tested and compared. Table 1 presents the results of the lost-in-the-middle task, showing the performance percentages of different models at various positions within the context. Each position index consists of 500 samples, and all results are derived from fine-tuning the Llama 2-7B model with 4K length data. The table highlights that cream consistently outperforms pose across different interpolation methods, indicating its superior ability to retrieve information from the middle of long contexts. Figure 3 presents the results of the long chat lines task, comparing the performance of cream with Llama 2-7b, RANPOS, and POSE. The results show that cream consistently performs best in retrieving information from long contexts, with an average performance improvement of 16% over POSE. As the context window size increases, the performance of all models tends to drop, but cream maintains its superiority, except at the 3.6K context window size. This demonstrates cream's robust ability to understand and retrieve information from extended contexts. Table 2 presents the performance results, % on the long bench benchmark. The table highlights that Cream 7B32K, which has been instruction tuned for just 100 steps using 4K length data on Llama 2-7B chat, surpasses several strong baseline models. Specifically, Cream 7B32K shows an average performance improvement of 1.6% over the second best model, Longchat v1.5-7B32K, despite being fine-tuned on a very small amount of data. This demonstrates Cream 7B32K's effective use of extended context size and its superior performance in long context QA and summarization tasks. Figure 4 presents the results of the needle in a haystack task, showing the recall performance of two models, Skipaline and Cream. The results are instruction tuned on Llama 2-7B chat with 4K length data. The color gradient from deep green to deep red visually represents the decline in recall performance, starting from 10 and decreasing to 1. This figure highlights the performance differences under varying conditions, providing a clear visual comparison of the model's effectiveness in this specific task. Table 3 presents the perplexity results for GovReport and ProofPile datasets, showcasing the performance of various models fine-tuned on different data lengths. Notably, Cream and POSE consistently demonstrate the lowest perplexity across different settings, significantly outperforming RANPOS. This discrepancy is attributed to the discontinuous position indices used during RANPOS fine-tuning, which creates inconsistencies with the pre-training stage. The table highlights the effectiveness of Cream and POSE in maintaining low perplexity, indicating their superior handling of extended context sizes. Table 4 presents the experimental results of standard benchmarks, focusing on the performance of Llama 2-7B fine-tuned on 4K data length. The table compares various models including RANPOS, POSE, and Cream across different metrics such as zero-shot and few-shot performance. Results indicate that Cream and POSE generally outperform RANPOS, with specific improvements noted in tasks like ArcC and HellisWag. The table also highlights the consistency of Cream with the original capabilities of the pre-trained base model, demonstrating its effectiveness in retaining and sometimes enhancing NLU abilities. Table 5 presents the perplexity results for the PG19 and Book 3 datasets, highlighting the performance of various models with different context lengths. Notably, Cream Linear 256K achieves a perplexity of 5.9, demonstrating its effectiveness even with extremely long contexts. In contrast, POSE Yarn 128K* shows a higher perplexity of 10.36. The table underscores the stability and performance of Cream across different target context lengths, indicating minimal perplexity increase with longer contexts. Figure 5 presents an ablation study of Cream on long chat lines, focusing on three main components: truncated Gaussian sampling, fixed start and end segments, and the trade-off between continuity and relativity. The study compares Gaussian sampling with uniform sampling, showing that Gaussian sampling leads to better retrieval performance. It also examines the impact of fixing the head and tail segments versus removing them or fixing only one, finding that fixing both segments performs best. Lastly, it evaluates the balance between continuity and relativity, demonstrating that balancing these properties yields the best performance. In the realm of efficient transformers, several methods have been proposed to address the limitations of local attention. For instance, FOT integrates memory attention layers to enable large models to learn from a wide context while reducing interference. Infini attention incorporates compressed memory into the standard attention mechanism, combining masked local attention and long-term linear attention. LLOCO employs LoRa with context compression and retrieval for offline learning. These methods extend the long context window but often require modifications to the attention mechanism or additional modules. In contrast, CREAM does not necessitate such changes and can be directly applied to pre-trained models. Regarding positional interpolation, Chen et al. Introduced a method to extend the context window by linearly reducing input position indices. Subsequent methods like NDK, ABF, and EBF modify the base frequency of rotary positional encoding. Yarn introduced a segmented interpolation method, and LongRoP utilizes non-uniformity in positional interpolation with a progressive expansion strategy. CREAM can be combined with any positional interpolation method. For positional encoding, RANPOS modified position indices to leverage the relativity of positions, and POS emphasized the importance of continuous segments. CREAM utilizes both relativity and continuity, enhancing the model's focus on the middle part of the context. In this study, the authors introduced the CREAM method, which is designed to extend the context of large language models. CREAM effectively balances the trade-off between continuity and relativity, allowing the model to fine-tune within the pre-trained length while maintaining closeness to the pre-trained state. The method employs truncated Gaussian sampling to concentrate on middle positions during fine-tuning, which enhances the efficiency of the process. Experimental results show that CREAM outperforms existing methods on both base and chat models, effectively addressing the issue of lost in the middle. Thank you for watching.